Welcome to Mathematics Educators Workshop at Home. Today we are looking at reduction formulae with the grade 11s. Now these learners were introduced to trigonometry in grade 10 using similar right-angled triangles in which ratios were sought in proportions. And further, trigonometric ratios were defined in a right-angled triangle. So let us look at that for a short time. So the trigonometric ratios, they were defined to these learners in grade 10 as sine of theta, which is abbreviated to sine theta, and cosine of theta, that is abbreviated to cos theta, and the tangent of theta, which is abbreviated to tan theta. Furthermore, these ratios were defined in a right-angled triangle as follows. So let us look at triangle ABC, in which angle B is 90 degrees. So the trigonometric ratio of sine, it is defined as the side, the length of the side opposite to the angle theta all over hypotenuse. So let's suppose angle C is theta. Therefore, in this triangle, angle C is therefore equals to the side opposite to the angle theta. Here it's AB. So this is AB over the hypotenuse, which is AC. So this will be AB over AC. The next one, we have cos of theta equals to the length of the side adjacent to the angle theta over the hypotenuse. So the side that is adjacent to the hypotenuse is this side, which is BC. Therefore, this ratio will be BC over the hypotenuse, in this case is AC. And the last one, it is the tangent of theta. It is given by the side opposite to angle theta, the side opposite over the side that is adjacent to angle theta. So in this case, this will be AB over BC. So all this introduction and definition of trigonometric ratios was done in grade 10. Now, we realize that these trigonometric ratios, they are only working with acute angles. If you look at those right angle triangle that we focused on, the only definition that we're focusing on is these acute angles. For example, where theta is. In this case, angle A is 90 minus theta. So these are the two acute angles that we defined the trigonometric ratios with. So why are we then talking about reduction formula? We're talking about reduction formula because when an angle is given as an obtuse angle or a reflex angle, that angle does not satisfy the conditions that we just went through now. So we need to reduce every angle that is bigger than an acute angle to the size of an acute angle that will give the same position of the terminal arm as that angle. So that is why we talk of reduction formula. So let's go and look at the questions that are given here to guide us develop the reduction rules. Now, the given statement says, give the size of an acute angle which gives the terminal arm the same position as angle 223. We are going to represent these angles at standard position so that we can be able to show the position of the terminal arms of these angles and therefore be able to identify the acute angle that gives the same position. So this angle here is 223 degrees. So it opened from 0 degrees, went by 90 degrees, 180 degrees. You have 270 here, and it completed revolution here. So the angle landed here in the third quadrant. So the question is, what is the size of an acute angle that will give the same position of the terminal arm as this angle, 223 degrees? Well, if we open the angle on this horizontal line here, the x-axis, towards 180, going in anti-clockwise direction like that, this angle here, it is an acute angle, and this angle also lands at the position of the terminal arm that is given by 223 degrees. So the question then is, what is the size of the angle that gives the same position as the terminal arm of 223 degrees? Now you simply say 223 degrees minus 180, and that it is 43 degrees. So that means the size of this angle here is 43 degrees. Therefore, we can therefore represent the 223 degrees as this angle is the same as 180 degrees plus 43 degrees, sine of 223 degrees. This is the same as having sine of 180 degrees plus 43 degrees. Now, this 43 degrees, it is that acute angle that gives the same position of the terminal arm as angle 223 degrees. What is then important is we need to identify, we say in which quadrant is this angle. This angle is found in quadrant number 3, but we know from our previous lesson that in quadrant number 3, only tangent is positive. Therefore, this is equals to negative sine 43 degrees. Why? Because in this quadrant, this angle sine is negative there. So sine of 223 degrees, it is the same as sine of 43 degrees. That is the acute angle that we were looking for. If I have cos of 223 degrees, this can be written 180 degrees plus 43 degrees. Now, we are saying this angle opened from 180 degrees, and the size of an acute angle that will give us the same position as 223 is 43 degrees. Therefore, this can be expressed as, in the third quadrant, we know that only tan is positive. Therefore, this will be negative cos 43 degrees. So cos of 223 degrees is the same as negative cos 43 degrees. Lastly, let's look at tan of 223 degrees. This will also be tan of 180 degrees plus 43 degrees. Now our acute angle is 43. Since we are in the third quadrant, tan is positive, so this will be positive tan 43 degrees. So this is how best we can represent the reduction of the size of an angle such as 223 degrees to an acute angle that will land at the same position. Let us look at the next angle, 123 degrees. So we'll represent that on a set of axes, negative 123 degrees. So this angle goes in clockwise direction. So it opens from 0 degrees, that is negative 90 degrees, negative 180 degrees, negative 270 degrees, and negative 360 degrees to complete a revolution. So this angle is negative 123 degrees. This angle, it is found in the third quadrant. It opened all the way from the horizontal line there and landed in the third quadrant. So we are looking for the size of an acute angle that will give the same position as this angle here. So that angle, so the angle that will give the same position is this one. Moving from this horizontal line towards the negative 180, going in clockwise direction. That it is the size of an acute angle that will give us the same position as this angle. The angle that is given is negative 123 degrees. So this is the representation of that angle. If I'm looking at sine of negative 123 degrees, I can simply write this as sine of negative 180 degrees plus 57 degrees. In the third quadrant, only tangent is positive. Therefore, this will give us negative sine of 57 degrees. Similarly, if I have cos of negative 123 degrees, this will be cos of negative 180 degrees plus 57 degrees. Now this, it gives us negative cos 57 degrees. Lastly, if I have tan of negative 123 degrees, this will be tan of negative 180 degrees plus 57 degrees. Now this is the same as tan of 57 degrees. Why? Because the tangent is positive in this quadrant. Now, one other way of doing this is, instead of finding only the size of the acute angle, one can decide to find the size of a positive angle that will give the same position as this angle. Now, opening the angle from right where this the angle of negative 123 opened from, all the way towards the position of the arm. So this complete a revolution. So what we can simply do is, we can simply say, if this angle goes in clockwise direction and landed here, so the size of this angle here is 237 degrees. Now, if we don't want to work with the negative angle, we can therefore simply express it in that way. Say, sine of negative 123 degrees is the same as sine of 237 degrees. So we can now work with the positive angle. So sine of 237 degrees can be expressed as sine of 180 degrees plus 57 degrees. And we say 180 plus the acute angle that lands us in a third quadrant. Therefore, only tangent is positive there. So this is the same as negative sine 57 degrees. Now this angle, it is the same as that one there, cos of negative 123. So this is the same as cos of 237. So it's cos of 237 degrees. It is the same as cos of 180 degrees plus 57 degrees. Now this will give you negative cos 57 degrees. This 57 degrees, it is our acute angle that gives the same position as the 237 degrees. Lastly, if we look at tan of 237 degrees, this is equals to tan of 180 degrees plus 57 degrees. Now this will simply give us tan 57 degrees. So this angle is found in the third quadrant, and in the third quadrant only tangent is positive. So let's go and look at 111 degrees. So what is the size of an acute angle that will give us the same position? Right here, going in clockwise direction. So that angle there will give us the size of an acute angle that gives the same position of the terminal arm as 111 degrees. Now, what is that angle? Now, you simply say 180 minus the 111 is going to give you that angle here. So that angle is going in clockwise direction, therefore it will be negative. So that is 69 degrees. So I can therefore represent this angle 111 as 180 degrees minus 69 degrees. This is the size of the acute angle that we are looking for. So I can now express this angle in this manner. If I am given sine of 111 degrees. So this can be expressed as sine of 180 degrees minus 69 degrees. Now, this angle is found in the first quadrant and only sine is positive there. Therefore, the acute angle is 69, so this will give us sine 69 degrees. So sine of 111 will give us the same value as sine of 69 degrees. Let us look at cos of 111 degrees. Cos of 111 degrees will still be cos of 180 degrees minus 69 degrees. Therefore, it is in the second quadrant. In the second quadrant, only sine is positive. Therefore, this is negative cos 69 degrees. So this will be the reduced angle. Lastly, we look at tan of 111 degrees. This can be expressed as tan of 180 degrees minus 69 degrees. So that leaves us with negative tan of 69 degrees. So that will be the reduced angle. Lastly, we are looking at negative 36 degrees. So sine of negative 36 degrees. Negative 36 degrees is the acute angle. It is found in the fourth quadrant. So in the fourth quadrant, only cos is positive. So this will be negative sine 36 degrees. Tan of negative 36 degrees will therefore be negative tan 36. And cos of negative 36 degrees will be positive cos 36 degrees. So this is basically the reason why we have to reduce the angles. We are reducing the obtuse angles or reflex angles to the size of an acute angle that gives the same position of the terminal arm as those angles. Let's look at question B. 180 minus 60 will get 120. So I can represent this as follows. Number 1 is sine of 120 degrees. It is the same as sine of 180 degrees minus 60 degrees. Now, sine of 180 degrees minus 60 degrees, 180 minus 60 is 120. Therefore, this 60 degrees is the reduction value. This is the reduced acute angle. Therefore, this angle is in the second quadrant. Our answer will simply be sine 60 degrees. So sine of 120 is equal to sine of 60 degrees. The second question, we are given cos of 210 degrees. Now 210 degrees is an angle that is bigger than 180 degrees. It is in the third quadrant. So you can simply say 210 degrees minus 180. So that will give you 30 degrees. So this angle therefore can be expressed as cos of 180 degrees plus 30 degrees. Now 180 plus 30 will give us 210. So that is the same as that angle there. Now our reduced angle is 30 degrees. In the third quadrant, only tan is positive. So this will be negative cos 30 degrees. Lastly, we're looking at tan of 315 degrees. Now 315 degrees, this angle finds itself in the fourth quadrant. Now in the fourth quadrant, 315, we can simply say 360 minus 315, and that gives us 45 degrees. So this angle can be expressed as 360 minus 45 degrees. So this is tan of 360 degrees minus 45 degrees. So the acute angle we're looking for is 45. Now in the fourth quadrant, only cos is positive. Therefore, the answer to this will be negative tan 45 degrees. Now, we are going to investigate the reduction formula for the general angles. Now, I always develop worksheets like this just to try and fast track the conceptual development with learners. A worksheet of this nature I give it to the learners and therefore give them several instructions that will aid them in completing the worksheet. Like if you look at the worksheet, the instruction is simple. Make the angle that is formed by the terminal arm OA angle theta, and use Pythagoras to determine the length of OA, and therefore write down the trigonometric ratios in that empty block up there. Now, once that is done, follow the transformation at the top of, and therefore reflect the terminal arm and the acute angle formed and the point accordingly. And therefore, I know that this is a knowledge that they acquired in the lower grade, in grade 8 and 9. Therefore, that shouldn't be a difficult work. Once that is done, they come back to class and we use what they have done to develop the concept of reduction. So, let us go and look at the first column. It says reflection about the line y-axis. That is, the line x is equals to 0. So we are reflecting the terminal arm AO about the line x is equals to 0. So if the point A is 3 and 1, when we reflect that point about the y-axis, that point is going to be negative 3 and 1. So the terminal arm will lie there and our acute angle theta is found here. Now we want to deal with the size of this angle. So if this angle is theta, what is the size of this angle here? Now we know if this angle was to reach all the way to the horizontal line here, this is 180. Therefore, the size of this angle up is 180. So this angle is 180 degrees minus theta. So that is the size of that angle. But this angle 180 minus theta, it gives the same position as the of the terminal arm as the acute angle theta at the bottom there. So what do we know? We already know the ratios that are given by sine theta, cos theta, tan theta. Sine theta is 1 over square root of 10, cos theta is 3 over square root of 10, and tan theta is 1 over 3. So now we're looking at the ratio of the trigonometric ratios for the angle of 180 minus theta. So this is sine of 180 degrees minus theta. Now, what does this equals to? Looking at the terminal arm in the second quadrant. So this it is equals to 1 over square root of 10. Remember, the length of the radius does not change. But what is 1 over square root of 10? 1 over square root of 10, it is equal to sine theta. So this basically is equals to sine theta. So our reduction rule is that sine of 180 degrees minus theta is equals to sine theta. Let us look at the second trig ratio, cos theta. So cos theta, in this angle we have cos of 180 degrees minus theta. This is equals to, now the value of x here is negative, so that is negative 3 over the square root of tan. But what is negative 3 over the square root of tan? From the original cos of theta, we found that cos theta is equal to 3 over square root of tan. So this is just a negative number. So basically this is equals to negative cos theta. So the reduction rule here is that cos of 180 degrees minus theta, it is the same as negative cos theta. So that is the reduction rule. And the last one, we have tan theta. So tan theta is equal to 1 over 3. But what is tan of 180 minus theta? So this is tan of 180 degrees minus theta. This is equals to 1 over negative 3. So that is negative 1 over 3. But tan theta is equals to 1 over 3. So this is equals to negative tan theta. Therefore, the reduction rule is tan of 180 degrees minus theta is equals to negative tan theta. So this will be our reduction formula when the angle is found in the second quadrant. Now, let's go and look at the next reflection. The next reflection says the angle and the terminal arm, they are reflected about the origin. So our angle here is angle theta. Dropping down the perpendicular here, we'll still find those values that we found in the first quadrant. We know that sine theta is equal to 1 over square root of 10, cos theta is 3 over square root of 10, and tan theta is 1 over 3. Now this angle, it is reflected about the origin. So in order for you to do that reflection, the point went 1 unit down and went 3 units to the right. So from the point of origin, I'll go 3 units to the right, 1, 2, 3, and 1 unit down. So the point will be here. So this line will be reflected there. So our reflected theta is there. So this is the image, which is negative 3 and negative 1. Now from here, we can now be able to find our angles. Now this is our angle theta. But what is the size of the angle that has opened all the way from our origin to there? So we know that this is 180 degrees. So the size of this angle will therefore be 180 degrees plus theta. So that is the size of that angle. Now, we therefore want to find the rule for sine of 180 degrees plus theta. What we know is that sine theta is equals to 1 over square root of 10. Now, the terminal arm length does not change, is square root of 10. So what is the ratio of sine of 180 minus theta? In this quadrant, that is negative 1 over square root of 10. But what we know is that 1 over square root of 10 is sine theta. Therefore, this is equals to negative sine theta. So our general rule can be written as sine of 180 degrees plus theta is equals to negative sine theta. So that will be the reduction rule. Now let us look at cos of 180 degrees plus theta. The cosine of 180 degrees plus theta, so this angle here will be negative 3 over square root of 10. But what we know is that 3 over square root of 10, it is equals to cos. So since this is negative, so this will therefore be negative cos theta. So our reduction rule says 180 degrees plus theta is equals to negative cos theta. The last one, we're going to look at the reduction of the tangent. Tan of 180 degrees plus theta is equals to, it is opposite over adjacent, that is negative 1 over negative 3. So that is positive 1 over 3. Negative divided by negative is positive. So what is 1 over 3? It is tan. So this is simply tan theta. So our reduction rule will say tan of 180 degrees plus theta is equals to tan theta. That is the reduction rule for the angles that are found in the third quadrant. Now, let us look at the last reflection line. Now, this reflection line, it says reflection about the x-axis. So, this is the reflection about the line y is equal to 0. Our coordinate point is 3 and 1. When we reflect it about the x-axis, it will then be the image of A will then be 3 and negative 1. So the point will be here. So if this is our angle theta, it is reflected about the x-axis, so theta will be dropped right there. So the length of our terminal arm is square root of 10. The coordinates are 3 and negative 1. Now, what is the size of this angle here? Now, the size of this angle, since this angle here, it is theta, and once it has come to the horizontal surface here, it would have completed revolution 360. So this angle here is 360 minus theta. So this angle here is 360 degrees minus theta. So what is sine of 360 degrees minus theta? Now sine of 360 minus theta, it will therefore be equals to negative 1 over the square root of 10. But what do we know about square root 1 over square root of 10? 1 over square root of 10 is equal to sine, but this answer is negative. So this is equals to negative sine theta. So the reduction rule for this will be sine 360 minus theta will therefore be equals to negative sine theta. Now, cos of 360 degrees minus theta, this is equals to cos is adjacent over hypotenuse, so that will be 3 over square root of 10. 3 over square root of 10 is cos theta, so this is cos theta. So the reduction for cos of 360 degrees minus theta will therefore be equals to cos theta. And the last one, we're looking at the tangent, so that will be tan of 360 degrees minus theta. This is equals to tan is opposite over adjacent, so that is negative 1 over 3. But what is 1 over 3 is the tangent, so this is negative tan theta. Therefore, our reduction rule for tan will be tan of 360 degrees minus theta. It is equals to negative tan theta. So this is the reduction rules for all the angles that are found in the fourth quadrant. Now, someone may ask, why did we all focus on the 180 and the 360, the horizontal line? Can't we find the size of these acute angles from the vertical line? And indeed we can, but that is a special case that we're going to look at it in just a moment. But let us just show what that means. All along, the angle that we've been focusing on, we opened our terminal arm from the horizontal surface. But this terminal arm that is drawn here, I'm now in the third column. I'm looking at the blue terminal arm that I reflected about the x-axis. Now, the acute angle that I marked it opening from the horizontal surface coming to the terminal arm here. But I can also mark it from the vertical line here going in clockwise direction. So this is also an acute angle, because if these angles, they are in the right angle triangle, so these angles here, they will be acute angles. Why can't we use these acute angles? No, we can. they just happen to change the trigonometric ratios to their co-function. So let's go and look at that. So the summary of the reduction formula that we just looked at is as follows. We're saying when an angle is found in the second quadrant, the reduction rule is 180 minus theta. When it's in the third quadrant, it's 180 plus theta. When it's in the fourth quadrant, it's 360 minus theta. And therefore, we say in the first quadrant, all the trig ratios, all the functions are positive. This is an exercise that you can give to the learners to practice more and more on reduction formulas. And then I just picked this from one of the textbooks that I'm using, Mind Action Series. So I'll give them the page number and they will attempt to that and we'll work it together. Now, reducing angles by 90 degrees and 270 degrees. So similarly, I design the same worksheet, give it to them, and ask them to follow the transformation statements above, and then we can discuss the following day at school. So let us look at this. The first reflection that I give these learners is about the line y is equals to x. But before we do that, let us complete the trigonometric ratios for this angle with the terminal arm that is given. Okay, now let us now follow the instruction. So this is the line y is equals to x. The learners are expected to reflect this point and the terminal arm about the line y is equals to x. Now, when you reflect about the terminal arm, so about the line y is equals to x, basically those coordinates just swap around. It is something they've learned in grade 8 and 9. If they are struggling, you can advise. So the image of A will therefore be 1 and 3, and that point lies here. So this is 1 and 3. Therefore, our terminal arm would have reflected through this point, and our theta is here. Now, if this is our theta, we're moving it from the vertical line, which is the 90 degrees. So that line is 90 degrees. We have 0 and 360 degrees. We have 180 degrees and our 270 degrees here. So we say, what is the size of this angle here? If this angle is theta, together this and that, they form 90 degrees. So the size of this angle, it is 180 minus theta. So this angle here is 90 degrees minus theta, because the two of them, they are complementary. So let us then go and look at our trig ratios. Sine of 90 degrees minus theta. Now sine, it is opposite over hypotenuse. So the length of the terminal arm is still square root of 10. So this will then be 3 over square root of 10. So this is our value of y, that is x. So those coordinates have changed. Now, what is 3 over sine theta over square root of 10? From what we have developed here in our original arm, 3 over square root of 10 is cos theta. So that means sine of 90 minus theta is equals to cos theta. So our reduction rules simply says sine 90 degrees minus theta is equals to cos theta. That is our reduction rule. Now, what is cos of 90 degrees minus theta? Cos of 90 degrees minus theta, it is adjacent over hypotenuse. So that is 1 over the square root of 10. But what is 1 over the square root of 10? 1 over the square root of 10 is sine theta. So this is equals to sine theta. Therefore, cos of 90 degrees minus theta is equals to sine theta. And then lastly, we look at tan of 90 degrees minus theta. Now tan is equals to opposite over hypotenuse over adjacent. So this is 3 over 1. Now 3 over 1, if you look at the original terminal arm, tan theta is equals to 1 over 3. So if you divide that by 1, you will get 3 over 1. Now this is simply the reciprocal of tan. And what is the reciprocal of tan? Is cotangent. So this is cot theta. Therefore, we can simply say tan of 90 degrees minus theta is equals to cot theta. So basically we can see that when we are reducing by 90 degrees, all these angles, they changes, the trigonometric ratios, they change to their cofunctions. So the cofunction of sine is cosine, and the cofunction of tangent is cotangent. Now, let us again look at the reflection of the image of the original A. So that means A, A2 prime. Let us go and look at that. And I'm just gonna write it here in the third column here. So we're looking at the transformation of A2 prime. Now, how do we get that? We are reflecting that point by the y-axis. So if we are reflecting this point here by the y-axis, it is 1 and 3. So reflecting this point about the y-axis will then be -1 and 3. So this will be 2 prime. It is -1 and 3. Remember, when you are reflecting about the y-axis, only x coordinate changes the sign. So this is our terminal arm, and therefore our theta is reflected here, and the length of the terminal arm is still square root of 10. Now, we are looking for the size of this angle. So let me draw that. So this is the angle we're looking at. Opening theta from 90 degrees, it is that way. Now, what is the size of this angle? So this angle will therefore be 90 degrees plus theta. So the angle is 90 degrees plus theta. Now let's go and look at the trigonometric ratios of that. Sine of 90 degrees plus theta. What does this equals to? Our terminal arm lies here by the point A2 prime. Now we know the ratio of sine is opposite over hypotenuse. In this case, our y is 3 and our x is -1. So this is going to be 3 over the square root of 10. But we know that 3 over the square root of 10, it is here, it represents the cosine. So that means sine of 90 plus theta is equals to cos theta. Now, what is tan of 90 degrees plus theta? Now, this angle is here in the second quadrant, so the ratio will then be y over x, so that will be 3 over -1. But from our first column, we saw that 3 over 1, that represented the reciprocal of tan theta, which is 1 over 3. But this is negative, so this is equals to negative cot theta. Therefore, the reduction of tan of 90 degrees plus theta is equals to negative cot theta. The last one, it is cosine. So we're looking at cos of 90 degrees plus theta. What is cos of 90 degrees plus theta. So it is adjacent over hypotenuse. And in this case, our x is -1 over the square root of 10. And from our original, we know that 1 over the square root of 10, it is sine. So this will therefore be negative sine theta. So cos of 90 degrees plus theta is equals to negative sine theta. So this is the reflection of our A prime about the line y-axis, or the line x is equals to 0. So this is when we are reducing by 90 degrees in anti-clockwise direction. Now, let us go and look at the reflection that follows in the second quadrant. Firstly, we're going to look at we're going to reflect this terminal arm of the original about the x-axis, just so that we can follow through before we go to the line y is equals negative x. So firstly, let us look at the reflection about the line y is equals to 0. So here is our angle theta. Our terminal arm is square root of 10, and therefore we are reflecting this terminal arm about the x-axis first. So when we reflect about the x-axis, our A prime will therefore be 3 and -1. So that point will lie here. So our A prime will be 3 and -1. So let us represent the terminal arm. So the reflected angle theta is marked there. Now, if we have this angle, we want to reflect this angle about the line y is equals to -x. Let us look at that line. The line y is equals to -x goes through this point. So this is the line y is equals to -x. We are reflecting our A prime through the line y is equals to -x. And that point, our A2 prime will lie here at 1 and -3. So here is our reflected point. So our reflected theta lies there. Now, this angle here is our theta. But what we know is that this is 270 degrees. Now, how can we get the size of this angle here? So this angle here is 270 degrees plus theta. So what is the size of that 270 degrees plus theta? Let us now look at the trig ratios. So this will be sine of 270 degrees plus theta is equals to, now the ratio of sine is y over the hypotenuse, and the hypotenuse is still square root of 10. So this will be -3 over the square root of 10. But then we know that 3 over square root of 10 is cosine. So this is equals to negative cos theta. So sine of 270 degrees plus theta is equals to negative cos theta. Now, what about cos of 270 degrees plus theta. Cosine of 270 plus theta. Now this is x over r, that is 1 over the square root of 10. But what is 1 over the square root of 10 from our original that is sine. So this is equals to sine, and they are both positive, so that is simply equals to sine theta. So cos of 270 degrees plus theta is equals to sine theta. Lastly, we're going to look at the tangent. So tangent of 270 degrees plus theta is equals to the tangent of 270 degrees plus theta. It is y over x, so that is negative 3 over 1. But then we also identify that this is a reciprocal of 1 over 3, so this will be negative cot theta. So tan of 270 degrees plus theta is equals to negative cot theta. Now, let us now finish with the 270 minus. Now, where do you get the 270 minus? Let us now go and reflect our A prime, A2 prime to A3 prime. Our A2 prime is 1 and negative 3. Now we are going to reflect this about the line x is equals to 0. We're reflecting the A2 prime about the line x is equals to 0, which is the y-axis. So our A3 prime will therefore be, if we're reflecting this point about the y-axis, we know that only value of x will change the sign. So that will be negative 1 and negative 3. So this point will lie here. So the angle theta will be reflected here. The coordinate of our A3 prime will therefore be equals to negative 1 and negative 3. Now, we are then going to find those trig ratios. So we look at sine of the size of this angle. Now, which angle are we talking about? So I'm just going to use a green pen so that the angles they can be clear. So what is the size of this angle of the green pen? The size of this angle is therefore going to be 270 degrees minus theta. So that angle will be 270 degrees minus theta. So let us look at those. It will be sine of 270 degrees minus theta. This is equals to, sine is equals to opposite over the hypotenuse, that is negative 3 over the square root of 10. And we know that 3 over 10 is cos, but it's negative. So this is equals to negative cos theta. So we can simply say sine of 270 degrees minus theta is equals to negative cos theta. The second one, we look at cos of 270 degrees minus theta. So this is equals to adjacent over hypotenuse, that is negative 1 over the square root of 10. And from our original we know 1 over the square root of 10 is sine. So this is equal to negative sine theta. So cos of 270 degrees minus theta is equals to negative sine theta. And lastly, we are looking at the tangent. So this will be tan of 270 degrees minus theta. This is equals to opposite over adjacent, that is negative 3 over negative 1, that is the same as 3. And therefore, now 3, it is just the reciprocal of tan, so that is cot theta. So we know that tan of 270 degrees minus theta is equals to cot theta. So basically, this way of developing the reduction rules using all this reflection or transformation concept and learners developing these rules by themselves, I believe will strengthen their understanding and they will not make any mistake. Now, from here, you give them an exercise that is based on reductions that are on vertical line. I just forgot to indicate the page number from which I got these questions, but this is the textbook that I'm using, the Mind Action series. Now, from here, they can be able to deal with any of questions that has to do with reductions. Now, let us look at these examples that I also looked at just to strengthen more learner understanding of reductions. The first angle that is indicated there is 290 degrees. Now 290 degrees, we can reduce that using the vertical line of 270. If we say 270 plus 20, that will give you 290 degrees. So this angle here, the fourth quadrant, only cosine is positive. So since this came from sine, this negative cos 20 degrees. So this will be the reduced value of this. Okay, let us go and reduce the next angle, which is 197 degrees. Now 197 degrees is found in which quadrant? This angle is found in the third quadrant. Now being in the third quadrant, we can reduce this angle by 180. Can simply say tan of 197. So simply say 97 minus 80, and that is 17 degrees. So this is the same as the sine of 180 degrees plus 17 degrees. Now 180 plus 17 will give you 197. So this angle is in the third quadrant, and in the third quadrant tangent is positive, so this will simply be tan of 17 degrees. We are reducing 197 degrees by 270 now. We say this can be expressed as tan of 270 degrees minus 73 degrees. Now, when you say 270 degrees minus 70 degrees, that is going to give you 73 degrees. That is going to give you 197. So our acute angle will therefore be 73 degrees. But 270 minus is in the third quadrant. Now this is going to change to the cofunction of this, which will then be cot of 73 degrees. Remember, the cotangent is the reciprocal of tan, which is the same as 1 over tan. So this, it is the same as 1 over tan 73 degrees. Lastly, we are looking at cos of 120. Cos of 120, this can be expressed as 180 degrees minus 60 degrees. Now, this angle is in the second quadrant, and therefore we know that in the second quadrant only sign is positive, so this is equals to negative cos 60 degrees. We can also reduce this by using the vertical line, which is the 90 degrees. So we can simply say 90 degrees plus 30. 90 degrees plus 30 will give us 120 degrees. So I can still write this as cos of 90 degrees plus 30 degrees. 90 plus 30 will also give us 120. So this is equals to, it is in the second quadrant, so only sign is positive there, so this will be negative negative sine 30 degrees. So negative sine 30 degrees is equals to negative cos 60 degrees, or is equals to cos of 120 degrees. And therefore you provide learners with some exercise for more practice to strengthen their conceptual understanding. You can give the learners more work on angles that are negative for them to practice, because one of the challenges that we are facing as teachers is that many of our learners, when they come across negative angles, they tend to make so many mistakes. Thus, it is advisable that as teachers, we provide learners with so many problems to practice and practice that involves negative angles. The other thing is revision of reciprocals. So this is a concept that they did in grade 10. You just have to remind them of the names of the reciprocals. The reciprocal of sine is cosec, cosecant. The reciprocal of cos is sec. The reciprocal of tan is cot. And then you express them in the in equation format: reciprocal identities and quotient identities. Tan of x can be expressed as sin x over cos x, and cot x can be expressed as cos x over sin x. Also remind them of basic trig identities that are developed using the terminal arm, that cos x plus sin x is equals to 1, and manipulating all that equation, you can find all these other trig identities. Talk about special angles. You can give them like this, or you can develop them. If you remember in grade 10, this is the diagram that we used to develop the special angles, so they still remember that. Now, one important thing that we now need to look at is trigonometric equations. Now, let's go and look at the equations and look at the usage of learners' prior knowledge in developing the concept of trigonometric equations. Now, here is the baseline task that one can develop just to try and build up to the important definitions of the trigonometric equation. One of the important trigonometric equations that the grade 11 learners are going to deal with is the concept of general solutions. So just take them back to grade 10, to different types of solutions they worked on, and therefore make use of that as a foundation to explain why we are now talking about general solutions. Right. Let us look at the first question that I set up here. X squared minus 1 is equals to x plus 1. They say, the instruction says solve for x. Now, solving for x in that equation is x squared minus 1 is equals to x plus 1. Algebraically, the equation will now be x squared minus x minus 2 is equals to 0. And then we factorize. The factors of this equation are this is x minus 1 times x minus 2. The bigger factor takes the minus sign, so this is x plus 1. Therefore, x is equals to negative 1, or x is equals to 2. So we have solved for x in that equation. Let us now look at question number 2. Question number 2 says, for what does your solution stand? For what does x minus 1 or x is equal to 2 stand? These values, they stand for they represent the x coordinate of the x-intercept of the two graphs. So in other words, we've got two graphs. I'm just going to give them names. F of x is equals to x squared minus 1, and g of x is equals to x plus 1. So in other words, we've got two graphs that are drawn together. Let me sketch the x squared minus 1. So it has a turning point at negative 1, and therefore the x-intercept at 1 and the other one at negative 1. So this is negative 1 and 1. And therefore we've got the straight line x plus 1, which has the y-intercept at 1, and therefore the x-intercept at negative 1. So the graph goes like that. So these two graphs, they intersect at these 2 points. There is this point of intersection and this point of intersection. What are the coordinates of this point of intersection? So this point is basically here on the x-axis. So the first one is x is equals to negative 1, and the other one is x is equals to 2. So these are the x-intercepts of those equations. Now let's go to question number 3. What does question number 3 say? They say graphically represent sine alpha is equal to 0.5 for the domain of alpha is the element of 0 to 360 degrees. So let me draw this graph here. So this is question number 3. We've got 0 degrees, 90 degrees, 180, 270, and 360 degrees. The graph of sine alpha, it has a maximum value of 1 and minimum value of negative 1. So this is the graph of sine alpha. I'll also give it a name. So I'll call this sine alpha. F of alpha is equals to sine alpha, and the constant line is g of x is equals to 0.5. So the line y is equals to 0.5 will therefore be this one. So this is the line y is equals to 0.5. Now what is happening is that these graphs, they intersect twice, at this point and at this point. What we need to do is we need to find the values of alpha at this point and that point. Now, the fact of the matter is that these equations, they are equal at these 2 points. So hence we have that equation. They say graphically represent that. Now, you can see that the domain is given as alpha is the element of 0 degrees to 360. What if the domain is not given? So that means the graph will continue waving up and down to the positive infinity, waving up and down to the negative infinity. That means these two lines, they will forever be meeting. Now, this is the reason why we start talking of general solutions. How can we find all these values where these two equations or these two graphs are equal? We then talk about the general solution. So we're going to talk about that now. I'm just going to put it up there. Example number 1, they say solve the equation sine x is equals to 1. Sine x is equals to 1. So graphically, okay, so this is the graph of y is equals to sine x. And I'm also going to draw the line y is equals to 1. So that line is a constant line that is passing through the y is equals to 1. It touches the graph at the turning point up there. They say solve the equations below. Now, if we want to solve this equation, we are given sine x is equals to 1. So we simply find the angle. That will be x is equals to the arcsine of 1, and that is equals to 90 degrees. So the arcsine of 1 is 90 degrees. Now, we therefore say that this angle, it is only the angle that appears in the first quadrant. So this line, these graphs, they also meet again at 270 degrees. They meet again at if the graph continues, they will meet again in the go back to the first quadrant just above 360, and then they will meet again when it goes in this first quadrant, continuing in the negative direction. So how best can we represent this? We simply say, in which quadrant do we find sine x positive? And that is in the first quadrant and in the second quadrant. So this angle is in the first quadrant. So we simply say it is 90 degrees plus 360 times k, for which k is the element of integers. What does this represent? This just represents whenever the graph goes back to the first quadrant, depending on the number of revolutions that it has completed. If we replace k with 0, it means that this is within the first revolution. We replace k with 1, it means that this is within the second revolution. When the angle complete the second revolution, then we'll be able to find the point of intersection between these two graphs in the first quadrant. Now, again, we therefore say that will be x is also equals to 180 minus 90 plus 360. So that will still be 90 degrees. But I'll just do it for procedure so that learners know that this is the step that they has to follow. So this will be 180 degrees minus 90 degrees minus that angle plus 360 degrees k, and k is the element of integers. So that is the way we deal with these equations. Let us go and look at the second equation. The second equation says sine beta is equals to cos beta. So that graph there still represents sine beta. Now cos beta, we know that cos of 0 is 1. So cos of 0 is 1. Cos of 90 is 0. Cos of 180 is negative 1. Cos of 270 is 0, and cos of 360 is 1. So the graph goes like that. So there are the two graphs. Now when these two graphs are drawn together, they have intersection at this point, just above 90 degrees but less than 180. They have intersection at this point, just between 270 and 360. And again, they have intersection here in the first quadrant, and they have intersection here in the second quadrant. Now, how are you going to deal with that? It is something that I will deal with just after we have dealt with basic way of dealing with general solution. Now, so if you look at this, one way of dealing with this equation is it is sine beta is equals to cos beta. If we divide both sides by cos beta, we get sine beta over cos beta. From those quotient identities, we see this is tan beta is equals to 1. Now, we have a tangent of beta is equals to 1, and we're going to look at all those forms of the trigonometric equations that involve general solutions of this. So if we are looking at this, we simply say beta is equals to the arctan of 1 plus k times the period of that graph, which is 180, and k is the element of integer. Now that still represents the same thing to say as in when the terminal arm moves around the point of origin, it completes the graph within 180 degrees. So this is 45 degrees plus k times 180 degrees, and k is the element of integers. So with this, we'll then be able to find the values of all those points where these graphs intersect. Now, let's just use this to find those points, and then we'll go and deal with the general solutions. This was just introduction to show why we talk of general solutions. So if I'm looking for those angles, the first thing that I'm going to do is let k be 0. When k is 0, beta is 45 degrees. So this angle here is 45 degrees, the first angle in the first quadrant. The second angle, it is found between 180 and 270. So what we simply need to do is replace k with an integer. So I'll replace k with 1. So that will be 180 plus 45 degrees, and that is 225. So this angle here is 225 degrees. And then on the other side, if you're looking for this angle, you simply replace k with -1, that is negative integer. So we have 45 degrees minus 180, and that gives us negative 135 degrees. And therefore, the next one is found in the fourth quadrant. Now, you can just replace that k with a second integer. So that will give you 45 degrees minus 360, and that is, this angle here is negative 315 degrees. So this is how the general solution works. Now let's go and attempt all the general solutions according to the trigonometric ratio specifically. So let's look at this. The solving trigonometric equation, the general solution of sine theta is equals to a, for a is the element of -1 and 1. Now, where is this -1 and 1 coming from? If you look at the sine graph here, it has the amplitude of 1. So that means the minimum value of this graph is -1 and the maximum value is 1. So if it happens that the number that we have here, it is smaller than -1 or bigger than 1, there won't be a solution, because the graph, if suppose the value of a is -1.5, so that graph will be moving below the graph. So these graphs won't intersect. On the other hand, if the value of a is above 1, so the graph will be moving up above the sine graph like that, and there won't be a solution. But if it is either -1 or 1, they will touch at the turning point. But if it is less than 1, they will have multiple intersections. So we say, how do we find the solution? So the first thing is you find the arcsine of that value. So that is a. So we have sine theta is equals to A. So theta is therefore equals to arcsine of A plus K times 360 degrees, and K is the element of integer. Now again, you also operate theta is equals to 180 degrees minus this answer, the arcsine of A plus K times 360, and K is the element of Z. Now, depending on the value of A, if the value of A is positive, you know that the angle is found in the first quadrant, and again you look at the trigonometric ratio. If it is sine, it is positive in the second quadrant, hence we say 180 minus. If it's cosine, it is positive in the first quadrant and in the fourth quadrant. And one other way of dealing with this, you can just find the reference angle for the cosine, and therefore you use the reflection. So let's go and look at that. Here we have the general solution of sine theta. So you simply write sine theta is equals to negative 0.47. So theta is equals to the inverse, the arcsine of negative 0.47. That is negative 28.03 degrees plus K times 360 degrees, right? And you also have theta is equals to 180 minus that is 151.97 degrees plus K times 360 degrees. Right. The other thing that we can also do is by using the quadrant in drawing up to this general solution. You can ignore the negative sign and simply find all the quadrants in which the trigonometric ratio of sine is negative. The trigonometric ratio of sine is negative in the third quadrant and also negative in the fourth quadrant. So you can also say theta is equals to 180 degrees plus 28.03 degrees plus K times 360, and K is the element of Z. So that is 180 plus 28.0 degrees. That gives us 208.03 plus K times 360. K is the element of integers. Again, you can say theta is equals to 360 minus 28.03, and that is 331.97 plus K times 360, and K is the element of Z. All these formulas, they will give you all the angles within which sine theta intersect with 0.47. So that is the general solution. And they say hence write down the values of theta between 0 and 360. So between 0 and 360, let's start with this one that has negative values. If I replace K with 0 here, it says theta is negative 28.03. So that angle is not in that quadrant. It's not within 0 to 360. I leave that out. If I replace K with 0 here, the angle I get is 151.97. So the first angle we get is 151.97 degrees. Now, I replace K with integers. If I replace K with 1 with the first equation, that will be 360. 360 minus 28.03, and that is, the other angle is 331.97. If I replace k with 1 in the second equation, that will be above, way above 0 to 360. So the only angle we have is 151.97. Now, if I go to the first equation, I replace k with 1. Okay. In the second equation, I replace k with -1. That will give me 151.97 minus 360. And that gives me the other angle of negative 208.03. On the other side, if you look at if I replace k with 0 on the equation of 208.03, I get 208. So the other angle is 208. So the only two angles that we have here is 208.03 and 151.97. These are the only two angles that are found within the intersection of these two graphs. Now, let us look at the general solution of the cosine. Looking at the general solution of the cosine, if you look carefully at the cosine graph, it is a reflection of each other about the y-axis. Okay, we now look at the general solution of cos theta. So we are looking at cos theta is equals to 1. Now, if you look at the rule here, applies to cosine just like it applied to sine. And what is important is that the value of a here, this constant, and the amplitude of the cosine graph, they are either equal or the value of a is smaller than that. Because if a is bigger than the amplitude, then those two graphs have no solution. If the value of a is bigger than the amplitude, then there is no solution between the two graphs. So, in this case, we've got cos theta is equals to 1. So the amplitude of this cosine graph is 1. So there is a solution here. So they meet at this point, they meet at that point, they meet at that point. So this is the only point where these two graphs meet. But when you look at this point, like let's start with the coordinate of point D. The coordinate of point D is 360 and 1. This point is a reflection of point M, which is negative 360 and 1, about the line x is equal to 0. If we look at the last point here, point T is 720 and 1. Is a reflection of point U, which is negative 720 and 1. So basically these two pieces of the graphs, they are reflections of each other about the y-axis. Therefore, in order to find the general solution of cosine, you can simply say theta is equals to plus or minus the arc cos or the inverse of cos of that constant, which is 1 times k plus k times 360, which is the period, and k is the element of integers. Now, what is the inverse of cos of 1? Is 0. So theta is equals to plus or minus. So it's just that I have 0. I cannot write plus or minus because there's no such plus or minus for 0. But if it was any other number, I'll write plus or minus because this is a reflection about the y-axis. So let us look at this. We have cos theta is equals to negative 0.538. So this will be cos theta is equals to negative 0.538. So theta is equals to plus or minus a cos of negative 0.538 plus k times 360. Now this is the arc cos of 0.538 is plus or minus 122.55 degrees plus k times 360, and k is the element of integer. Or you can also use the quadrant and say in which quadrant is cosine negative. Cosine is negative in the second quadrant and the third quadrant. So you can also write theta as theta is equals to 180 minus 122.55, and that angle is 57.45 degrees plus k times 360, and k is the element of z of integers, and theta is also equals to 180 plus 180 plus 122, that will give you 302.55 plus k times 360 degrees, and all those general solutions will provide you with all the answers or the solutions for the intersections of these two graphs. The last one, it is the tangent. So this is the rule for the tangent. You simply find the arc tan of the given number a, and therefore since the range of the tangent is from negative infinity to positive infinity, so it doesn't matter, there will forever be an intersection. Now if you look at this, they say solve for theta if tan theta is equal to 1.465. So this will simply be theta is equals to the arctan of 1.465 plus k times 180 degrees, and k is the element of integer. Now that angle is 55.68 degrees plus k times 180 degrees, and k is the element of z of integers. Now if you want to also consider the quadrant, you can simply look at the value there. Tangent is positive in the first quadrant. This will give you the first quadrant angles, and therefore the angles in the third quadrant, that will be theta is equals to 180 degrees plus 55.68 plus k times 180. So that is 235.68 plus k times 180 degrees. So all these general solutions, they will give you all the answers for which tan of theta intersect with the line y is equal to 1.465. Now, if you also take the learners back to grade 11 to practice with equations, these are basic equations that somewhere somehow requires the use of their knowledge of acute angles, and then take this to grade 11, change angles to cofunctions and so forth. So these are more and more practice work. And the other thing that we're going to look at is working different types of equations that can result into general solution. Now, let us look at type 1. Type 1, we are given sine 2 theta plus cos 2 theta is equals to 0. So this is the equation. You can transpose the cos 2 theta. You have sine 2 theta is equals to negative cos 2 theta. And from here, divide both sides by cos 2 theta. And therefore, this gives you negative 1. You've got tan 2 theta is equals to negative 1. And therefore, 2 theta is equals to negative 45. The arctan of negative 1 is negative 45 degrees plus k times 180 degrees, and k is the element of integers. And we divide both sides by 2. That will give you negative 22.5 degrees plus k times 90 degrees, and k is the element of integers. So that will be the general solution for the equation that appears in the form of this type 1 equation. Now, one other thing that we also look at is the type of equation that involves taking out the common factor. Let us look at type 2 equation. So type 2, we're given 2 sine alpha cos alpha minus cos alpha is equals to 0. So with this equation, you can see between these two terms there is a common factor of cos alpha. So you can take it out. You've got cos alpha, you are left with 2 sine alpha minus 1 is equals to 0. Therefore, cos alpha is equal to 0, or 2 sine alpha minus 1 is equals to 0. So this is sine alpha is equals to 1 over 2. And the arcsine of 1 over 2 is 30 degrees. So this will be alpha is equals to 30 degrees plus k times 360. K is the element of integers, or 180 minus 30, that is 150 plus k times 360, and k is the element of z. And the arcsine of cos 0, that is 90 degrees. So this is alpha is equals to 90 degrees plus k times 360, and k is the element of z. So since it's a cosine, you can simply write plus or minus 90 degrees plus k times 360, and that will give you all the angles. Now, let's go and look at type 3. Type 3, we are given an equation that involves working out equation in a grouping format. Some method of factorization that these learners did in grade 10. We're given 2 sine beta cos beta minus 6 sine beta minus cos beta plus 3 is equals to 0. Now when I look at this equation, I've got cos beta plus 3 here. Between these two terms, I can take out the common factor of 2 sine beta. So in these two terms, take out the common factor of 2 sine beta. We'll be left with cos beta minus 6 divided by 2 is 3, minus, between these two terms I take out negative 1. I'll be left with cos beta minus 3 is equals to 0. So we have the factors 2 sine beta minus 2 sine beta minus 1 times cos beta minus 3 is equals to 0. Therefore, 2 sine beta minus 1 is equals to 0, or cos beta minus 3 is equals to 0. And therefore, from here you can follow the general rules. Now, let us look at the fourth type. The fourth type, we're given sine squared beta minus sine beta minus 2. It is in the form of a trinomial. So the coefficient of sine beta here is 1. So this is sine beta minus 1 times sine beta minus 2 is equals to 0. The bigger factor takes minus, so that is the case. So you've got sine beta is equals to -1, or sine beta is equals to 2. And from here, you can also apply the general rules of general solution. Let us now look at type 6. Type 6 is another form of a trinomial. So we're given cos squared theta plus sine theta cos theta is equals to 1. Now, we know that from the trig identities, one can be expressed as sine theta plus cos theta. So this is cos theta plus sine theta cos theta minus 1 is equals to 0. So in other words, this is cos squared theta plus sine theta cos theta minus sine squared theta plus cos squared theta is equals to 0. So this is cos squared theta plus sine theta cos theta minus sine squared theta minus cos squared theta is equals to 0. Now cos squared theta minus cos squared theta is 0. We are left with sine theta cos theta minus sine squared theta is equals to 0. And which takes us back to the common factor method. There is a common factor of sine theta. We are left with cos theta minus 1. Cos theta minus sine theta is equals to 0. So sine theta is equals to 0, or cos theta minus sine theta is equals to 0. And therefore, you can just manipulate this as cos theta is equals to sine theta. Divide both sides by cos theta, cos theta. Therefore, we have tan theta is equals to 1, and we can apply the general rules. Now, let's go and look at type 7. Type 7, we're given sine theta is equals to cos theta. Now here they are encouraging the use of the cofunction. If you look at the first one, we know that sine theta is equal to cos of 90 minus theta. Therefore, instead, if we're given sine theta, we can replace that as sine of 90 minus theta. Now, if these trig ratios are the same, therefore the angles should also be the same. Otherwise, these are not equal. Therefore, you have theta is equals to 90 minus theta plus k times 360. And k is the element of z. Taking the theta this side, 2 theta is equals to 90 degrees plus k times 360. And k is the element of integers. Divide both sides by 2. That will give you 45 degrees plus k times 180 degrees, and k is the element of z. Right. Um. So these are just various methods of dealing with the general solution. If you look at type 8, it also talks about the core function,